Going to look at some applications of vectors to finding the work done by a force and the moment/torque of a force. So one use of vectors, specifically the scalar product/dot product, occurs in physics in calculating the work done by a force. So in one dimension, where what I mean by one dimension is you move an object over a distance d using a constant force F, and the work then is equal to distance by force. Now usually that's written force by distance, but we'll see why there's a reason I write it the other way around. In more than one dimension, things are a little bit different. For now, suppose we have a constant force. Suppose however that the constant force is a vector pointing in some other direction than the displacement. So in other words, if it's not just one dimension, suppose this goes like that. This is the displacement vector. So the object goes from the top from here to the top. And suppose the force looks something like this. And I think we're going to name these points. We'll call this the point P and this the point Q, so that the displacement vector is the vector from P to Q, which is Q minus P. So the thing about the work done by this force given by the black vector there, the bit of the force that is perpendicular to displacement does no work whatsoever. So if I call this F perp, that doesn't do any work. Work is, as far as I understand, giving energy to something, and that perpendicular force doesn't give energy to it, whereas the other force, the parallel part, does. So this is the force parallel. So, and we can find using our trigonometry. Now we'll go through it here just because I think there's plenty of time in this lecture. So if theta is the angle between the displacement and the force, and the length of the force vector is the magnitude of the force vector, then the work done is equal to the magnitude of, and actually I'm going to do it the other way, so it'll be the distance, which is the magnitude of the displacement vector, times the magnitude of the parallel vector. Now we can find the magnitude of the parallel vector going over on the left and doing a little bit of trigonometry. So the cos of theta is adjacent over hypotenuse. Adjacent to theta is the magnitude of the parallel force divided by the hypotenuse, which is the magnitude of the force. And so we find, by multiplying both sides by the magnitude of the force, the magnitude of the parallel part of the force is the magnitude of the force times the cos of the angle. So we get that the work done, so this is just a one-dimensional work, distance by force. But if we work with it a bit more, we see that the magnitude of the parallel part of the force is, the magnitude of F times the cos of the angle in between. And we've seen this formula before. So we have that. So we'll write what we're going to write here. So we showed that the work done by a force is the magnitude of the displacement that the force puts the object through, times the magnitude of the force, times the cos of the angle in between. But as I said, we've seen this before. This is the dot or scalar product of the displacement with the force vector. So work is equal to displacement vector dot or scalar product force vector. And notice that what you get out is a number. Work is a number because it has units of energy, and energy doesn't have a direction. So just to kind of visualize, and there's another thing you can look at there. Okay, so let's do some examples. So I've been thinking a little bit more about the assessment, and what I'm thinking is, because it's open book, I'm probably going to make the questions a bit hard, and I'm probably going to student number personalize them for reasons. So that's probably what we're looking at. I think with this, I will be giving you notice of this as well. Okay. So let's see an example here. So consider a body moving from this point A to point B, where distances are measured in centimeters. We're engineers, we need to be careful with units. There are 3 forces acting on the body. Assume they are measured in newtons. So find separately the work done by each of the following forces as they act on the body. So I'm just going to write these down for myself. I'll pause the video. Okay, so I have the 3 forces written down by my side. So didn't write down the point. So work is given by the dot product of the displacement and the force vector. Okay, so I'm going to better go back and get the displacement vector. Here are the points. So I'm just going to pause again. Sorry. So I'm just going to write down the points. So the point A is 1, 2, minus 4, and the point B, we're going to the point B, which is 6, 7, 8. Now we are going to do this B minus A business, right? But just notice here, it's actually easy enough. Just actually here, see it. How do you get from 1 along the X to 6 along the X? You go plus 5 along the X. How do you get from 2 along the Y to 7 along the Y? You do plus 5 along the Y. How do you get from minus 4 along the Z to 8 along the Z? You do plus 12. So we're going to see that the displacement vector is this. Just say that. Okay. So the displacement vector. So we'll draw a little picture, see what we're doing here. So essentially you have, draw it up here. You have a displacement. And there's 3 forces acting that we know of. So I'll just draw them here. So say we've got force 1. We have force 2, say. And suppose we've got force 3. Now force 3 can do work there. It would just do negative work. So you can have a body going from, oh yeah, should have drawn the A and the B. So here's A and here's B. You can have a body going from A to B with force 3 acting. That's no issue. Like imagine the trolleys have picked up fierce speed, and then force 3 goes against that and it'll slow it down, but the trolleys will still move. All you're doing is you're taking energy out. So it isn't a contradiction that force 3 does work. Okay, so the displacement here is the vector from A to B, which we said is B minus A. So the displacement vector is A to B, which is B minus A. I write those lines underneath to signify that these points aren't exactly the same as vectors. They kind of are in a way, but not exactly. And I don't just leave it as B and A, because B and A typically might be numbers. Okay, anyway, B is 6, 7, 8. And A is 1, 2, minus 4. They're given in the question. 6 minus 1 is 5. 7 minus 2 is 5. And 8 minus 4 is 8 plus 4 is 12. And we've seen this up here. So now we're going to calculate the work done by the first force, the second force, and the third force separately. That's what the question is looking for. Find separately the work done by each of the forces. Okay, so the first one we'll call W1 is the displacement dotted with force 1. So the displacement is 5, 5, 12. And what about this first force? Now it's 6i plus 3k. That means 6i means 6 along the x. Now there's no mention of j, so it's 0 along the y. And 3k means 3 along the z. Okay, so you get 5 by 6 is 30. Plus 5 by 0 is 0. Plus 12 by 3 is 36. And we get 66. Now we want to do units. Now I'll tell you something which is nice. If you have a good formula, so for example here, displacement by force, and now I'll just write A and B, right? So A and B are some quantities that you're multiplying together, and these square things mean the units. The units of A times B will be the units of A times the units of B. Similar story. Let me give a different situation. So for example, the units of velocity. Now what's velocity? It's a change in distance over time. Now I'm just going to say it's distance over time. I'm going to make things a bit easier for myself. And you can show in a similar story that the units of distance over time are units of distance divided by units of time. And the units of distance in SI certainly are meters, and the units of time are seconds, so you get meters per second, which can be written like that, or like that. Now the point I'm getting at is if you're looking at the units of distance by force, now I appreciate it's a dot product, it's a little bit different, but just maybe trust me that the units stay the same. Basically what you have is you get the units here, 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 and you add them together. It's like apples and apples. Now what you want to do is you want to multiply the units of the distance by the units of the force. Now usually we'll use like Newton meters or whatever, so we'll do force first. Now if you read the question, it said newtons, and then the distance, it said centimeters. Now there will be a mark going for this. If you want to kind of know what you're doing, you can convert that to meters. For example, 66 centimeters is 0.66 meters, and you could go to 0.66 Newton meters. And then you might know that a Newton meter is a joule, and give me 0.66 joules. Now, what I'm saying is that at a minimum, I want some units that are correct. You do not have to do the conversions. I'm quite happy with this, even though this is probably the best. But I'm quite happy with Newton centimeters. Okay. Let's find the next one. So the work done is the dot product or the scalar product of the displacement with the second force, which is still 5, 5, 12. Dot product, the second force is minus 6i, 2j, and minus 3k. So you get 5 by minus 6, which is minus 30. 5 by 2 is 10. And 12 by minus 3 is minus 36. And I think I'm getting minus 56. And I'm just going to go here with Newton centimeters. You could go with centijoules. We won't do that. We'll just go with Newton centimeters. I'd probably turn it into joules, but I don't seem to have the space. And then the last one, the work done. Now, notice there's no arrow on the, you don't have an arrow on the work because the work is a number, not a vector. So the third bit of work is the displacement dot product with the third force. 5, 5, 12, dot product, the force is 0 minus 2, 0. And so you get 5 by 0 is 0, plus 5 by minus 2 is minus 10, plus 12 by 0 is 0. Remember, 0 times anything is 0. And 0 minus 10 plus 0 is minus 10 Newton centimeters. Right. So that's calculating the three works. And then we have another question which says, I'll be up the top here, sorry. Why couldn't the net force have caused the body to move from rest from A to B? So consider the following true statement. So I'm saying this is true. In order to get from A to B, either another force was applied to the body or the body had an initial velocity. Okay. Now, you could get to A to B without another force, because obviously if you've initial, like even with the trolleys, imagine the trolleys are moving and you do nothing at all, then they can still move from A to B. But if, I'm saying, well, what if it has no initial velocity? What if it's initially at rest? I'm saying that to get from A to B, there must have been an initial force. Now, the question is, why couldn't the net force have caused the body to move from rest to B? So I think the best thing here would be to maybe calculate the net force. So the net force, which is the sum of the forces, so I'll just write them all out here. So 6i, no mention of j, 3k, plus minus 6i, 2j, plus minus 3k. By the way, don't put the i's in these brackets. You do one or the other. A mix of them, as I'll explain if any of you do it in the feedback, is not good. And so we get 6 minus 6 plus 0 is 0. 0 plus 2 minus 2 is 0. And 3 minus 3 plus 0 is 0. So the net force is 0. So the net force is 0. And remember that force is equal to mass times acceleration. And so the force being equal to 0 implies the acceleration is equal to 0, which implies no change in velocity. Now, we're going to just forget really about if it has, so we'll assume that it has the velocity equal to 0. If the initial velocity is 0 and the acceleration is 0, that means the velocity does not change. So that means the velocity for all times is 0. And if you've no velocity, cannot move, cannot change position. Displacement from A to B. So I do appreciate that is a bit more difficult. I think that was an exam question. I'd say anyone who said that the force was 0 was getting full marks. So like the question says, consider this: in order to get from A to B, either another force is applied or the body initial velocity. So if initial velocity, there's nothing to show. Sorry, I missed this bit. From rest. So that means the initial velocity was 0. So could this force move it? No, because the net force was actually 0. Now, if you add up the works, you get 0 as well. So this force does 0 work. So that means this force, the net force, does not give it any energy. And so if it's at rest and it's not given any energy, it cannot do anything. That's basically what we're talking about. Now, there could be other forces that give and take energy, but that's what the question says. There has to be another force. I think anyone who basically just noticed that the force of 0 is getting the marks there. Okay, example 2. A wire rope winch located at B pulls a wind turbine blade from A to B. The tension in the rope has a magnitude of 260 kilonewtons and is in the direction of A to B. So we might just draw that. So the tension force is in the direction of A to B, and the magnitude of the tension force in kilonewtons is 260. Okay, so throw in the kilonewtons. Find the force. Oh, sorry, it's not called T. We're calling it F. Should have called it T. Would have been better. Okay. Find F in terms of IJK. Okay, no bother. Hence or otherwise find the work done by the winch in pulling the blade from A to B. Okay. Now there's different things you can do here, but in advance, what you should do is see the vector A to B. You should find a unit vector in the same direction. I'll exaggerate it. So this would be the vector from A to B, hat. So that'd be a vector of length 1 in the same direction as A to B. And if you do that, what you can say is the force vector is equal to 260 times AB hat. So AB hat is a vector of length 1. It's in the right direction. And if you multiply a vector by a constant, a positive constant, you do not change the direction. And obviously this thing here, so we actually use something else, that the magnitude of a constant times a vector is equal to the absolute value of the constant, which is just going to be 260 over here, equal to the magnitude of times the magnitude of the vector. So for example, 260 AB hat is equal to absolute value 260, which is 260 times AB hat, but the way AB hat is designed, it has a length of 1. So 260 AB has the correct magnitude, 260, and it has the correct direction. So that's what we can do. Now we might just end up with a nice little shortcut as we go. So I'm going to, Okay, now as I've done all this here, we're probably going to do it on the next page as well. And we might see a shortcut as well. All right, let's see. So first we find A to B, right? Because we're going to find AB hat. So the first thing we want to do is find A to B. So the vector from A to B is equal to point B minus point A. Point B, you can see on the previous page, is 90, 20, 40. Take away A is minus 30, minus 10, 0. So you get 90 minus 30 is 120. 20 minus 10 is 30. And 40 minus 0 is 40. So that's the vector from A to B. Now we want to get the vector of length 1 in the same direction. So what we have to do is, if you want to get a vector of length 1, you take this and divide it by its own length. So we have to find the magnitude of A to B. Pythagoras says it's square root sum of the squares. So 120 squared plus 30 squared plus 40 squared. And those of you who know your Pythagoras triples, 30 squared plus 40 squared will have to be, your 3, 4, 5 will be 50 squared. And then you've got a 5, 12, 13 triangle. So if you bang all that in, you get that this is 130. Okay, so bang that into the calculator, I mean. So AB hat is equal to AB, which is 120, 30, 40, divided by its own length. And so the force, as we explained on the previous page, would be 260 times AB hat like this. Now you can multiply in the 260 and then divide by 130. And of course that's the same, if you multiply by 260 and divide by 130, that's the same as multiplying by 2, because 260 divided by 130 is 2. So you end up with 240. That's 2 by 120. 2 by 30 gives you 60, and 2 by 40 gives you 80. So that's part 1 done. There is another way of doing that. Once you recognize that the magnitude, say, of AB is 130, you might see the relationship between 130 and 260. And so if you wanted to get a magnitude 260 vector, you just multiply that by 2. Which we've essentially seen already. Now you might say, how is the force vector, longer than the vector from A to B? But of course, they're different units. Like, you can't really compare them. The vector from A to B is measured in meters, but the force is measured in kilonewtons. Like, there's no comparison. They're on different graphs, essentially. Okay, so we have the force anyway. And then the question is, hence or otherwise. And we'll go back and look at the otherwise in a moment. Find the work done by the winch in pulling the blade from A to B. So we've got the force. The displacement is, it's pulling it from A to B. We have the vector A to B up here. And so what we can do is, we've already found A to B. I mean, look, I don't know why I'm drawing it again. It pulls it from the bottom to the top. So the displacement is the vector from A to B, which we already calculated, was 120 along the X, 30 along the Y, and 40 along the Z. So we simply calculate work is the displacement. Now here, this is in bold, by the way, rather than the arrows. The displacement, scalar or dot product with the force. So you get 120, 30, 40. Dot product, the force is written above. 240, didn't really leave much space here. 60, 80, and I'm just gonna, so that didn't really leave much space here. Let's use a different color just to, so this thing is equal to, sorry about the space, 120 by 240, 30 plus 30 by 60 plus 40 by 80. If you bang all those numbers into the calculator, you get 3, what do you get? Be careful here, 33,800. I'm just copying from below, I know you get that. Now again, look at units. So the units of force was kilonewtons, and the units of distance was meters. So kilonewton meters, not kilonewton per meter, that's a different thing, kilonewton meters. There is or otherwise is, if you note that the displacement, which is this vector here, is in fact parallel to the force, you're back in the one-dimensional situation. You could just multiply the distance by the force. The distance is the magnitude of the displacement is 130, by the magnitude of the force is 260, you get the same thing. There's a bit of messing around here, right? So the kilo is 1,000, and so you've got 1,000, that's a 10 to the 6, that's a million, and a million is a mega. So that's the conversion between them. So basically this is 33 by 1,000, that's 33,800,000 by Newton meters, and then you divide out the million and you get 33.8 megajoules, the joule being the Newton meter bit. But I'm quite happy with kilonewton meters. Okay, so I think that's everything I wanted to say about force.